Hi, we are from Group 4. Today we are going to present Module 2, Linear and Radial Heat Transfer.
There are two parts to this, the linear conduction and the radial conduction unit. For the procedure, we have to first prepare the filler table. And during the experiment, we should ensure that the power supply is off and the voltage is set to zero. And we connect the thermocouple sensors to the heat transfer service unit and mount the specimen in and tighten the tension screw on it to make sure it is in place and does not move around. Water supply is turned on for the cooling and redirected to a outlet. After that, we turn on the power supply uh, and rotate the voltage controller to 30 volts. Then we can switch to the sensor displays to record the temperature. This is repeated for uh, 50 volts, 70 volts, and 90 volts. And this is all the same for the radio conduction unit. They just have a different set of thermocouple sensors to connect to the heat transfer unit. Cooling is on, power supply is turned on, and the voltage is set to 30 volts, 50 volts, and 70 volts. And between every change of voltage, we should let the specimen cool down before we continue.
So these are the tools and apparatus that we use in this experiment. First one is H112 Heat Transfer Service Unit. Second one is H112A Linear Conduction Unit. H112B Radial Conduction Unit. And the next one is the thermocouples for us to measure the temperature. And the specimens that we use are 25 mm diameter aluminium, 25 mm diameter stainless steel, and 13 millimeter diameter brass. And we also have the cooling water supply to prevent the apparatus from overheating.
Variable control. In this experiment, the controls variables are the material dimension, which is the length, diameter, and thickness, and the power supply, which we keep constant. The independent variable is the type of material that we test, such as brass, aluminum, and stainless steel. The dependent variables, however, are the thermal conductivity values and the temperature readings, which change depending on the material. This setup let us see how different materials affect heat transfer.
Now we move on to the expected results. The experiment conducted validates the Fourier's law. At 0 watts baseline, it stays flat confirming static thermal equilibrium with the room when no energy is supplied. The heat in radial brass moves outward because the area grows while the heat is constant. The local heat flux decays, resulting in a distinct curved logarithmic decay that flattens out completely at the outer radius. While for the linear heat conduction, heat travels through the fixed area. This proves lower conductivity such as steel drops continuously, while high conductive materials such as aluminum spreads the heat quickly. There are errors in this data due to thermal contact resistance, transition state reading due to capturing the data in unstable state, and finally, environmental heat loss. Now, moving on to the graphical data. For the radial heat conduction brass, the heat dissipates outward from the inner radius to the outer radius. It shows a distinct curve that moves steeply near the center and flattens out completely at the outer boundary. In linear heat conduction, theoretically, it should create a straight temperature on the gradient line. For that reason, aluminum transfers heat rapidly, forming a flatter high temperature line, while stainless steel, however, resists that heat flow, generating a steep and continuous drop.
Next, moving to safety awareness, When conducting this experiment, our primary concern is handling the high temperature generated by the H112 service unit. To prevent thermal burns, we must never touch the heating section or specimens directly during operation and always allow the apparatus to completely cool down before change material. Additionally, ensure all electrical connections are secured with dry hands when adjusting power inputs and handle the thermal paste safely to avoid any skin irritation.